We're going to pick up where we left off in the last video. This is the problem that we were looking at. I did have time to go in there and change the superscript that was having problems on the last video, so it looks a little different, but it is little f of t is the quantity t squared plus 1 squared, and g of t is 4t times the quantity t squared plus 1. So again, it said determine whether f of t is an antiderivative of g of t. So if that's the case, if f of t is an antiderivative of g of t, then when I take the derivative of f of t, I should get g of t for the answer. So let's see. Let's take the derivative of f. The power pops down front. Don't change what's inside. Reduce the power by 1 times the derivative of what's inside. So when we clean it up, it looks like this, and that is indeed g of t. So yes, f of t is an antiderivative for g of t. And so if we were asked a question like that, that's what we would do. And you have to be careful on the notation. All right, so let's talk about the general family of functions whose antiderivative is this antiderivative we're going to find, and we'll talk about notation. Hopefully you remember when we talked about the mean value theorem for derivatives that says that big F and big G are two functions such that when I take the derivative of f and I take the derivative of g, they equal each other for all x on some interval that we're looking at, I, of all real numbers. Then there exists some constant c that is the difference between f and g for all x in that same interval. And I don't know if you remember or not, but we drew a picture and we said, okay, if this is f of x, then something on the order of this would be g of x. In other words, what we're after is that the slope of the tangent line everywhere on the interval that we're looking at, the slope of the tangent line is the same on those two functions. And so on the original functions f and g, they only differ in the plane vertically by some constant c. So this distance, everywhere I look, no matter where, what x input I look, that distance between f and g is that constant value of c. So we're using that idea when it comes to the antiderivative because we're starting with the derivative function and we're taking the step backwards. So this shows that once we find an antiderivative of f, then we have found all the antiderivatives, an entire family of functions whose derivative is big F prime. And we may be looking for one specific member, meaning we'll have to figure out or will be shown what that constant value was in the original function that went to 0 when we differentiated big F. But this is the entire family of functions whose derivative is big F of x. So this is the antiderivative. So that's a little more formally what we talked about earlier, the difference between any antiderivative, which would just be a member of that family. We're going to talk about finding the antiderivative, so we're going to have to remember to put plus c. So here's a question: must a function always have an antiderivative? Well, if that's the case, let's think about that. If that's the case, then every function that we look at, whatever that function is, if it is to have an antiderivative, every function that we are looking at is a derivative function. Well, is it true then, let me ask you in the opposite direction, does every function have a derivative? And we've seen no. Not every function has a derivative over an entire interval where we might be looking. If this is an interval that includes x equals 0, then that derivative is not going to exist. So since not every function has a derivative, then in general we're going to say no, not every function is going to have an antiderivative. Here are some examples. We'll kind of explore the properties of integration, or the definite integral, by finding the antiderivatives of these functions. Now, I'm not calling f prime. I'm just giving you some function f of x and asking you to find the general antiderivative, or the antiderivative, of the function f of x equals x to the 7th. So what should we call the antiderivative function? Well, we can call it anything we want to, unless we're specifically told what we're supposed to. So let's call the antiderivative function g of x, so that when I take the derivative of g of x, I get f of x for the answer. Remember this question. This is an excellent question. What did I take the derivative of to get this for the answer? What did I take the derivative of to get x to the 7th for the answer? Well, using the power rule for integration, I know that the antiderivative function has to look like that. Okay, so that's a lot like the examples we've been doing. Let's go to this next one. Find the general antiderivative of f of x equals 4x to the 5th. Well, when I took the derivative of g, I popped my constant out front, and then I took the derivative of what was left. So when I reverse that operation, I'm going to do the same thing. I'm going to pop that constant 4 out front, and then I'm just going to concentrate on the meat of what's left, which is x to the 5th, and find the antiderivative of that term. I'm always going to remember to put my constant of integration, or my plus c. We could clean this up. This is now 2/3 x to the 6th plus c. So find the general antiderivative of f of x equals 4x to the 5th plus x to the 7th. I didn't fix that one, did I? That's supposed to be a superscript 7th. The antiderivative. So the question is here, does integration break up over addition? Because if it does, we can clearly see it's just going to be this antiderivative function plus this antiderivative function plus my constant of integration. And since differentiation breaks up over addition, it turns out that antidifferentiation will as well. The antiderivative of that term we just found up there was 2/3 x to the 6th. Copy down my plus, since integration breaks up over addition. And the antiderivative of this term, x to the 7th, we already found, was 1/8 x to the 8th. And there could have been a constant on there, so we've got to remember to put our constant of integration. So here, doing this example, we've already determined a rule or a property of the definite integral, and that is that it breaks up over addition, and not surprisingly, it breaks up over subtraction as well. So let's move on to the next one. Find the general antiderivative of f of x equals 3 cosine of x. This is where that question that I have up there comes in really, really handy. What did I take the derivative of to get cosine for the answer? Now, once again, I have popped my coefficient out front, my constants out front, because I can do that in differentiation. That means I can do it in integration as well. And so now the question is, what did I take the derivative of to get positive cosine of x for the answer? Well, that was sine of x. So the antiderivative for that function is 3 times the sine of x. And again, there could have been a constant in the antiderivative function that when we took the derivative, the constant differentiated to 0. So let's look down here on this last one. Find the general antiderivative of f of x equals 3 cosine x plus 4 sine x. Well, we've already determined what the antiderivative was for that first term. We've already determined that integration or antiderivatives break up over addition. So now we're going to pop our constant out front, and we're going to ask ourselves our question above about that function. What did I take the derivative of to get positive sine of x for the answer? And that was negative cosine of x. And again, don't forget your constant of integration. When we have sine and cosine, the positive and negative signs could have a tendency to kind of give us a headache. So make sure that you know that the derivative of sine is positive cosine, and the antiderivative of positive cosine is positive sine, right? These work in both directions here. The derivative of negative cosine would be positive sine. So the antiderivative of positive sine is going to have to be negative cosine. So make sure that you have those positive and negatives straight in your head. Again, another great argument for flashcards, because if we know them in the derivative direction, it's not that difficult to learn them in the antiderivative direction, but we sure want to make sure we get those positives and negatives straightened out in our head. All right, so let's talk about terminology and symbols. If big F is an antiderivative of little f, then big F plus c will be referred to as the indefinite integral of f. The indefinite integral of f is the antiderivative function plus the constant of integration. Now, since I don't want to have to write the words find the antiderivative of every time I want you to find the original function given a derivative function, then there is this symbol mathematically. This is from Mr. Leibniz. He came up with this symbol. It's kind of an elongated S. And every time you see this symbol, what it says to you is find the antiderivative of. This means find the antiderivative of, and then you're going to be given a function that we want you to find the antiderivative of. So that's what that symbol means. That is the integral sign, and it is the integral for the indefinite integral. We have some more things here. There is a term now for the derivative function in this context, and it's called the integrand. All right, you really won't see that, I don't think, so much on the AP test, but in the interest of teaching, that is, in this context, what it's called. This dx is playing a role, and we'll see in a minute how important that dx is, the role that it's playing. It's the variable of integration. It is the variable with which we are going to find the antiderivative for the integrand, and we'll talk a little bit more about that in a little bit. Big F of x is the antiderivative function. And we always have to remember to include the constant of integration, because when we take the derivative of that function, there could have been a constant there, and the constant could have gone to 0. So this notation, the integral of f of x dx, is read as the integral of f of x with respect to x. That's with respect to. Integral means find the derivative of. The differential notation in this context means this is the variable with respect that I want you to find the antiderivative. Now, we learned when we were doing differentiation and taking derivatives, when we did implicit differentiation and related rates and so forth, the with respect to variable, the dx or the dt, played an important role. It told us what variable with respect to take the derivative. That's what this is telling us in this notation. If I have f of x that doesn't just involve one variable, I only want to find the integral or find the antiderivative with respect to one variable. So I'm going to stop there. We'll pick the lesson up in the next video.